It's time now for our last hypothesis test for Chapter 10. Oh, there are more coming, don't worry, but this is the last one for Chapter 10, which is the hypothesis test for either the population variance or standard deviation. Matter of fact, I'll throw that in there right there. Okay, so this is a different test in a couple big respects. One is that you only have two main requirements. It has to be simple random sampling, as usual, and it has to be normally distributed. There's no n greater than 30. There's no n times p times 1 minus p is greater than 10. Those were available to us in the t-test right here, and the one prop z test right here. But they're not available to us in the test for the variance or standard deviation. They're just not going to be there. All right, then I've kind of joined them up together. They're basically the same problem over and over and over. So what I mean by that is that this is the same test for either variance or standard deviation. All that is different for them will be your hypotheses. So I kind of have these reversed. Actually, I'm going to flip these. So the variance is the sigma squared, or the sigma on its own would be just plain standard deviation. And then I'll kind of reverse all of them and fix that. One second. All right, there we have it. So the variances are the ones in the front. The standard deviations are the ones in the back. And they're going to work exactly the same way. It's just a question of which hypotheses are you looking at. Then you select your level of significance alpha. You've got a test statistic formula right here, which is chi0 squared, etc. Then you have your choice of a classical approach or a p-value approach. Now the issue with the p-value approach is that the TI calculator does not find this as a standard issue test. So we are going to work with chi-square tests with the calculator, but it's not going to be this particular test. So we would have to look at computer output or something like that for this. Also keep in mind for the two-tailed test, you can kind of use the chi-square table to figure out whether your chi0 squared is on the left or the right. And that'll make sense when we get to an example that deals with that. And then if you're doing the classical approach, which will be pretty standard for us if we're doing it by hand, because we don't have the calculator option available to us, then it's one of these three graphs. Then you'll compare your critical values just like in the other ones, but now you're comparing them to chi-square values instead of t's or z's. Remember that the test for the mean involved t values. The test for the proportions involves z values. The test for variance or standard deviation, however, involves chi-square values. So 3 different distributions for 3 different kinds of tests. Oops, right there. And then we'll state our conclusion just like we always have. There is sufficient evidence, there is not sufficient evidence, etc. Okay, so the graduate record examination is a test required for admission to many U.S. graduate schools. Student scores on the verbal reasoning portion are said to have a population standard deviation of 120 by the company that makes the test. You don't believe them, you think that they're up to something, and you want to test their value of 120. So you collect a random sample of 10 scores, and the values are below. So here they are, right here. All right, and then I've drawn for you this normal probability distribution. So, well, first thing we need to know is, are each of the requirements for conducting a hypothesis test satisfied? All right, so the 2 requirements are it has to be a simple random sample and it has to be normally distributed. Those are the 2 requirements, no ifs, ands, or buts. No greater than 30, none of that stuff. So we know it's a simple random sample because it's given to us back here. It says that it's a random sample right there, so I highlighted it for you. So since it's a random sample, we know that that's the case. Then normally distributed, question mark? Well, yeah, the graph shows us, remember we learned these graphs in 7.4, they were everybody's favorite time because they're so simple. It shows us that the distribution of the data set is normal. All right, so the answer is yes. We've got yes on both and we are happy campers. We can now conduct a hypothesis test. All right. What is the sample standard deviation and what is the sample size? Well, to find those values, we would enter these data points into our calculator. Of course, I've given it to you here, but perhaps not with as many decimal places as we would like. So let me go grab the calculator. I'm going to go to Stat, Edit. I'm going to clear out this old data set from an old problem. I'm going to type in the new data set. So 489, 564, and so on. All right, I'll pause you and I'll enter the data set. There, I've got the data points in there. Then I'm going to go to Stat, Calculate One Variable Statistics. L1 is fine. And then press Enter. And then you can see that the S is 105.44619. So I'm going to type that in down here. All right, I'm going to make sure, just for our own benefit, we need to really know the symbol here. So I'm going to put that in there, that we have to know its symbol, which is S. Now, what is the sample size and its symbol? Well, you could count them real easily in this particular problem, but it's n equals 10. You can also just count the dots on the graph. There's 10 of them, right? Okay, so n equals 10. All right. Okay, so now notice the formula for the test statistic is chi0 squared equals n minus 1 times s squared over sigma 0 squared. All right, so let's remember from chapter section set 3.2, it's been a long time. S squared is the sample variance. Remember how we stressed variance back then? And then sigma squared would be the assumed population variance. It's assumed to be true in the null hypothesis. I'm just going to abbreviate that with POP, P-O-P, to get it all to fit in there. Actually, no, I won't. I'll just make it have a smaller font. It'll be fine. There we go. All right, now, is there sufficient evidence to conclude that the standard deviation is different from 120 at the alpha equals 0.05 level, significance level? Use the classical method. Alrighty then, we're doing it. The whole 6-step process. Step 1, we need some hypotheses. Now you can write these one of two ways. They're talking about the standard deviation. So you can write H naught, which is sigma equals 120. H1 would be that sigma, now did they say different? Did they say less than? Different. All right, so by saying different, that means we're doing a two-tailed test here. So sigma is not equal to 120. Now that's one way to write these, or let me just throw this in here. You could write it and then let me find 120 squared just for my own benefit. 120 squared would be 14400. So you could write sigma squared equals 14400, and then sigma squared is not equal to 14400. Those are both perfectly valid ways to write the exact same thing. Both are valid. Pick one, right? So it doesn't really matter which one you use, just as long as you use one of them. They mean the exact same test. Okay. Now I imagine for this particular problem, because it's talking about standard deviation right here, because that's the case, this is probably the one you're going to go with. But the other one is just as valid if you wanted to do it. All right, step 1 is done. Step 2, we need to choose our alpha. Well, actually, we won't choose them, not in the course. I mean, in real life, you get to choose it, but here it's given to us somewhere, 0.05 right there. So we know that alpha is 0.05. Good. Everybody's favorite step. It's always given. Step 3, we need our test statistic, and there is no calculator to do this work for us. So we're going to have to do it by hand. All right, there's the formula for the test statistic. It comes right out of step 3 when you look at the formula. Right here, step 3, right there. Okay, so we're going to have to go put in all the values we know right into the formula. All right, so n we know is 10. So this will be 10 take away 1. S squared we know is, oh no, what was that number? 105.44619. Okay. So 105.44619 squared. Of course, the more decimal places we keep for the S, the more accurate we're going to be. And then sigma squared, sigma is 0. Because it's 0, it's the null hypothesis, which is 120 squared. All right, so we need to go find these numbers. So let me grab a calculator. I need 10 take away 1, or you could just take 9, it's fine, times 105.4. Oh, let's not do this. Let's do it with the SX, shall we? I mean, we ran the calculation. So let's look at variables. Number 5 for statistics. And see number 3 right there? It'll know the last SX you found. So it's SX squared. Delete that. All right, so that gets us this number. Now, just on a side note, if I did 10 take away 1 times 105.44, I gotta remember the number, 446, let's just do 446. 446 squared. Let's see how different they are. There, they're really close together, so that's not too bad. They round up to about the same number, 1,00070. I'm going to use the more accurate number because I can. I mean, I have the power of the calculator behind me. Don't forget how I did that. I went to stat, so 10 take away 1, or if you could just you could just say 9. It's fine. 9 times, and then I did variables, number 5, which is statistics, then number 3, which is SX, and I squared it. Remember, this only works though because I've already run one variable stats here. It runs it off of the last, it memorizes, if you will, the last time it ran it. So it knows that that's 105.446. All right, I just redid this calculation so you can see it. And remember, we already know that 120 squared is 14400, 14,400. So now we need to take 100070.1 and we need to divide it by 14400 in order to get our test statistic. So it's 6.949. So I take this and I divide and I get 6.949. That is the test statistic right there. That's step 3. There you go. Beautiful. As a matter of fact, it all fits in a line. All right, so now we need step 4, which is going to be our graph. Now remember, you're drawing a chi-square graph. You do not want to make it look symmetric. It isn't. So let me draw that graph. I'll be right back. All right, so here we have the distribution, and of course it's right skew distribution because that's the way the chi-square distribution is. And now we're going to need to find these two values. Now I've obviously found them, but you're going to need to know how I found them. So let's keep in mind that it says right in the two-tailed test inferential statistics sheet right here. If you look at the two-tailed test, it says you need alpha over 2, then you need chi-squared 1 minus alpha over 2, and chi-squared alpha over 2. So we're going to need to spend some time figuring out a couple things. First thing we need to know is our degrees of freedom. Degrees of freedom, if you remember, is n minus 1, which is 9. So that'll be the row that we go to in our table. Then we need alpha over 2. So remember that alpha was 0.05. That means that alpha over 2 is 0.025. And that means that 1 minus alpha over 2 will be 0.975. So those are the columns we're going to go to in the table, the chi-square table. So let me grab the chi-square table. I want to go to the row number 9. 0.975 is 2.7, and 0.025 is 19.023. So that's where these numbers come from. I have 1 minus alpha over 2, that's 2.7, and then 19.203. This means that for step 5, we are not going to reject the null hypothesis because our test statistic, which is chi-square equals 6.949, is not in the critical region. That's those two gray tails. In other words, it's between the two chi-square values, and that's what I wrote here mathematically, that it's between the two numbers. And therefore, we're not going to reject. That means that there is not enough evidence to support the claim that the standard deviation of GRE verbal scores is not 120. This one's a little bit hard to write up for step 5, so you can talk about it being between the two values, or you can say it's not in the left tail nor in the right tail, which those are called the critical regions collectively. Personally, I find it easier just to write it that it's between the two. and you could write it that way if you wanted.